Hello, in this tutorial video I will show you how to create a new project in phievo, and the main goal is to first bias initial condition for your evolution. So for instance, you might want to impose an initial topology and also changing parameters of the simulations. So you should run the project creator notebook. So I've already started it, and I will show you how to what it contains. So here I'm going to try to bias the evolution of some mitogenesis. So the first thing to do is to enter the project name that you want to create. So let's call it somite bias. And then once you have started this notebook, you will have several tabs appearing here where you can define, customize your parameters. So I've already changed a bit the parameters to make them match what I want to do. So for the somite case, I only want to evolve transcriptional networks. So I'm just defining things related to transcription, such as random gene is going to be the relative rate to add new transcription factors to the network. This is the relative rate TFL, the relative rate to add a transcriptional interaction to the network, and so on and so forth. This is the relative rate to remove interactions. Of course, again, the goal is for you to customize all these parameters. Kinetic parameters, it's the same. You can customize them. So again, you can change them as you wish. So for instance, for some mitogenesis simulations, it might be a good idea to add a delay in transcription, so I put it to 10. Restart, you should not touch it if you're not an advanced user. General simulation parameters. So this is where you're going to specify things like the size of the population of networks that you're going to define. So I put it to 50. For embryonic problems, the number of cells you're going to specify, so 40. By default, it's going to be 1, but if you're looking at an embryonic problem, you want more cells in an embryo. Number of generations for the simulations, so typically 500 is good. Other things, number of inputs, of outputs in your network. So time step, number of time step, this depends on the specific problems, and this depends on the fitness function and the input function you define. So I just copied the one from the examples of the somitogenesis simulation that we are providing in the software, 0.01, 12,000. And then there are other things. So number of trials, this is a number of initial condition you want to test. So for instance, if you are doing a stochastic simulation, you might want to have several tests and average the fitness function. But if you only have deterministic simulation, one trial is good. And the other important thing is related to this recompute networks. Again, if you have deterministic simulation, you don't want to recompute network from one generation to the other, so you should toggle off this thing. So if you toggle it on, it's going to recompute the fitness every generation. If you toggle off, it will remember the fitness at the previous generation and will not recompute it. Okay, so that's it for general simulation parameters. So now the two most important parts are the initialization network part and the C5 part. So in the initialization network tab, you basically define, you can define a new network topology to bias the evolution. And so you have two parts. You can first add genes or species and then add interaction. So let's just add first genes. And so in the somitogenesis case, so we're going to start by adding one output gene on which the fitness will be computed. And so you see the network here. Later on, we will plot it, but first you have a list of what is added. So we had a species, this is called S0. This is my first output. Then I have my input, I add it. Okay, so this is added here. And now let's say I want to add another gene, another transcriptional factor. So this is a transcriptional factor. I can simply add it, and it works. Okay. So now what I want to do, I want to add interactions. So I'm going to bias the evolution by adding some transcriptional interactions between those genes. So I'm going to add a couple of interactions. So for instance, you might want that the input activates both genes, other genes. So let's say I want S1 activates S0. And so by default, the transcriptional interaction is going to be random. The nature is going to be random, but if you want to really specify parameters or types, you can just say click this custom parameters, and then this is going to be activation. And so these are the parameters of the activation. Let let's put them as they are. So we simply add them, and this add an interaction between S1 and S0, and let's add a couple of other interaction. So let's do the same where the input is activating the second gene. Okay. Okay, sorry. Okay, and I add it. And then let's do, for instance, maybe the two genes S0 and S2 might repress each other. So let's say S0, S2, I customize them again to have them repression. And so then I can specify parameters. So maybe let's start with a relatively high repression. So N is the Hill coefficient of the repression, and H is the threshold, sorry, the threshold of the repression. So let's add this. And maybe let's add a repression in the other direction where S2 is repressing S0. Maybe let's put something a bit milder. Okay, and then maybe to help a little bit again the evolution, let's assume that S0 is going to repress itself like this, and so TF S0 is repressing gene S0. This is going to create a negative feedback loop that could be of interest for evolution. Okay, and then I add it. Okay, so I have everything I want. I have three species, S0, S1, S2. S1 is the input, S0 and S2 are genes. And then S1 activate S0, S1 activate S2, S0, S2, S2, S0, they are repression. You will see in 1 second, and S0 repressed S0. So let's plot the network to see if this is consistent with what we've chosen. Okay, so that's a good network topology. S1 and activate S0, S2, S0 self-repress, and then neutral repression. So my networks will be initialized, my evolution will be initialized with those topologies. And now the last important part is the definition of C files. So the C files, this is where you define things like fitness function, init history, input functions, which is the dynamics of the input. So this is where you need to unleash your creativity for different problems, because obviously what you evolve depends on the fitness function. So by default here, I'm simply going to use my SOMITE fitness function as providing in the software in the examples. So you can download the examples. This is explained on the documentation. And so here I have located this C file there. So what I need to do, I just need to essentially fill out where the corresponding C files are. And so let's do that. So this is here in the example SOMITE directory. So the init histories, this is called init history 0 for the SOMITE case. And then for the input, this is init, same thing, same story. Input SOMITE. Okay. So now I've done that, and so you should not be afraid. These files will be taken and copied in the directory where the evolutionary simulations will be performed. So you won't lose anything. There is no risk to spoil these files, corrupt these files. Okay, so now we're ready. We have defined everything, and so now we can simply click on Write Project. And so what it does, it creates all these files. And then all this initialization thing, all this initialization file in directory SOMITE bias. And so now if I look at where I am, okay, so we are in phievo, and so now I have created this directory SOMITE bias. Okay, and in the SOMITE bias, I have my C files, and I have, most importantly, the initialization.py file, and I'm just going to show you what it looks like. I can edit it. And so it contains everything I have defined. So the parameters here, the mutation rates, the location of the C file I'm going to use for evolution, and then all my other parameters. And here, init network is the initial network topology. And so now, to run this simulation, I'm simply going to do as usual, as indicated in the documentation. I'm just running Python, and we're good to go. The simulations are working. Okay, so that's it for this demo. And thank you for listening to me, and I hope this is useful.